Welcome guys. Yeah, so this video should be the final video of the ring. Okay, so I want to talk about a particular ring. Particular ring, which is a Euclidean ring, is the Gaussian integer. So Gaussian integer. And then we will use the Gaussian integer to prove the theorem proved by Fermat. Basically, it's a p if the p is the prime, which is a form of 4n plus 1, then the p can be written as the integer square, two sum of integer squares. So for example, 5 can be written as 1 plus 4. And I think 13 can be written as a 4 plus 9. Okay. So any p is prime if it's form of 4n plus 1 can be written as a sum of two square of integers. Okay, so this is the number theory results, and we can use the Gaussian integer to prove. Okay, and so this is the Euclidean integer, Euclidean ring. So define a Zi. Basically, it's a plus bi, where ab is integer. Okay, so this is called a Gaussian ring. Gaussian ring. Okay, so your exercise for you is to prove Zi is a ring. This is a commutative ring, and with identity. So identity just one. Okay, and you can ask about also. Okay, so yeah, so in order to prove that it's Euclidean ring, we need to give it the norm, right? So give x, if x is a plus bi, then I define x to be a plus b, a squared plus b squared. And also check that for your own exercise checklist. Okay. And I think this is trivial, right? This is just the complex plane, the norm of the property of complex plane, right? So easy to check that it satisfies this. Okay, so also you can check that for d of x greater or equal to 1, right? For any z, because this is just x squared plus a squared plus b squared. So in order to make this to be, in order to make x to be a unit, the only way is that a is 0, b is plus or minus 1, or a is 1, b is plus or minus 0. Okay, so these four are only, these are all the units. So all the units are just all these four numbers. Okay, so from here, we can get the d of x is a non-negative integer for x non-zero. Also, d of x less than d less or equal to dxy for all y non-zero. And also, okay, so this is first 1 and 2. And the third, so these are all easy, right? And the third is a little bit difficult. Suppose you take the two Euclidean two Gaussian integers, and then you can find you can do the division, okay, such that v equals to tu plus r, such that r is 0 or d of r is less than d of u. Okay, so only at least one is difficult, right? Because the first two are just I think you can do from your elementary school, okay? Not elementary school, right? But from your, I think from your high school. But for only this one is a little bit difficult. This one says that you can do a division, okay? So what I'm proof is that I want to use the geometrical view, right? So you can view this is your xy plane, and the Gaussian integer is basically a plus bi, right? So you can plot all the Gaussian points here on, right? So this is all the points. Okay, so what this saying is that if you take any number u and v, right? U and v, and you can find that v equals to tu plus r, such that r is 0 or basically dr less than du. Okay, so I think what it means is that this is v, right? You want to find you want to find some Gaussian integer which is the multiple, you times v, then it becomes another Gaussian integer. So somehow like you can you want to make sure that it change. Okay, so suppose so if you times t, right, it's somehow like this v will change you to another, and you want to make sure it's very close to u, right, such that their difference is difference. Sorry, it's difference. Yes, this is u, this is v. So you want to make sure that this t times u, v minus t times u should be less. This is v, right? This is u. So you want to find your Gaussian integer, which is you change when you times t, it becomes another Gaussian integer, right? You want to check this is distance. This r should be less than this u. Okay. Yeah. So this is the number 3 is the most difficult property. Yeah, I think yeah. So I mean, there's a way one can use a geometric to prove it. Yeah, but I somehow not I somehow forget about it. Yeah, but fine. Let's prove it by algebraic way. Yes, I somehow remember that some people said that if you can draw some circle. Okay, so you can draw a circle for each Gaussian point of radius 1, and if it cover all the complex plane, if there's no point which is outside a circle, then it will be Euclidean domain. But somehow I forget why. Okay, so we need to prove it by algebraic way. Okay, so if y, so let's say the i's, let me just give a notation called r. Okay, so let's say if y, take y in r, and x is just a positive integer. X is a positive integer. Okay, and suppose y equals to a plus bi, then we can use a division algorithm, right, to write a to be to be un plus u1, and b to be vn plus v1, where u1 and v1 are integer. Set, so I can control u1 to v1 to be less than n divided by 2, right? So that's, yeah, so this is n. Okay, sorry, this is n. So I can make u1 absolute value of u1 less than n divided by 2, v1 less than n divided by 2. Okay. So then just let t to be u plus vi, and r to be u1 plus v1i. Okay, so you see now let's compute. So one can check that y is a plus bi just equals to, so I write a is so un plus u1 plus vn plus v1. So this is just u plus v n. So there's I here. So u plus vin times plus u1 plus v1i. Okay, so now we got division, right? We got division, and this is our r. So the norm of r is basically, or the d of r is basically u1 squared plus v1 squared, which is less than n squared divided by 2. Okay, so definitely less than n squared. Okay, so that means this work. Okay, so this for the so we work for general, we work for the specific integers. Okay. Okay, so now we go to general case, right? Suppose you get x non-zero, and the y is arbitrary element, and you want to do the division, right? So check that. So you notice that your x bar is an integer, right? Positive integer. Okay, and then we can, so we do the same thing. That we do a same computation, right? But for y x bar. Okay. Okay, so okay, so Let's see. So our result says that we can find TR in a ring, such that such that the y-x bar is Tn plus R with R0 or dr less than dn, right? And we get n is x bar, right? So from here that we get our dyx bar minus ttx bar less than dn, which is dx x bar. Sorry, let me just. Let me just make everything clear. So n and this is n and yeah dn, which is dx x bar, right? So from here and then we got this, right? So and we also, and this is dx bar, right? So I mean, well, I can easily say I can cancel this, so simplify into dy minus tx, because I can cancel dx bar, right? It's less than d of x. Okay, so we just let the y equals to tx plus r0, where r0 is y minus tx. Okay, and the t and the r0s, yeah. So obviously that these t and r0s are in the original Gaussian integer. Okay, so either r0 is 0 or d of r0 is d of y minus tx less than dx. Yeah, so algebra proof basically proves the general n, and you just do the listings. Yeah, I think this is somehow a geometrical idea if you go back to this picture and try to figure out why this is the case. Okay. Okay, so our final results is basically this Zi is a Euclidean ring. Okay, so once you have this or you believe this, then you can prove the following lemma. This lemma says that if p is an integer, so p is a prime number, and if there's a c which is a relative c in R, which is in this Euclidean domain relative to prime p, which means that their GCD is 1. And also then let's see. So yeah, suppose we can find x y is basically integer, such that x squared plus y squared equals to cp for some c, for this c. Okay, so that means you can find some Gaussian integer such as cp equals to x squared plus y squared for some for two integers. Then p can be written as x squared plus y squared for x 0 squared plus y 0 squared for some x0 y0s are integer. Okay, so what I'm saying is that if you have this hypothesis, then your prime number p can be written as the sum of two squares. Okay, and let's prove it. Oh, so this proof is simple. So let's see. So one can write cp as x minus yi x plus yi, right? So since p is prime, so either p is xyi or px plus yi, right? But p is a real number, right? So if p divides this, then the only case is p divides x and p divides y, right? Okay, but the problem is but the problem is that if p divides x, p divides y, then the p will divide x plus yi, right? So if this is true, then you will prove that p squared, right? Because p divides this and p divides this, so p squared will divide cp, right? Which will show that p divides c, which is a contradiction, right? Right? Okay. So which tell you that and if this is for the first case, right? In the second case, if you have P divides X and P divides Y, right? Then you can also show that the P divides X minus YI, then you will lead to the same conclusion, right? Because by say C is a coprime to P, right? So this now is a contradiction. Okay. So what it means, what this means is that this P cannot, so let me just write down, P cannot be a prime in Gaussian integer, right? Because what I'm saying, what I originally say is that P is a prime number, right? Prime number in the Z, but the P may not be factorized. P may not be prime in a Gaussian integer, right? But now in this argument, I prove that P cannot be a prime in a Gaussian integer. But if P is prime in a Gaussian integer, then it will lead to a contradiction, right? So which tells that since P is not prime, right? So one can write it as P as A minus A plus BI, and then let's say G plus DI, okay? But P is a real number, right? So if you take conjugates for both sides, you get this, okay? Right? So you can times this. So get P squared equals to a known, right? So A squared plus B squared, G squared plus D squared. Okay, so and then this, since P is not prime, right? P is not prime. So A squared plus B squared cannot be 1. And the G squared plus D squared cannot be 1. Otherwise, there are units, right? So there are units. So otherwise, they are unit. Okay, so since it's prime, right? So prime means it's not prime. So it's not prime means that you can write it as a 2-element product, which is none of them are unit. Okay. Right, so I get this. Okay. So now, obviously, right? If P, so now what one can ask. So now P is actually prime in the number theory in the original integer Z, right? So either we have P divides A squared plus B squared, or P squared divides A squared plus B squared, or yeah, but that's it, right? Because P is real prime. Okay. But basically, you already write a prime number squared into 2 products, right? So there are only several cases. So, okay, so the first case that this is P squared, this is 1, right? Or this is 1, this is P squared, or PP. Okay, right? This is the only case. Okay, so obviously that if A squared plus B squared is P squared, then G squared plus D squared is 1, right? But this is contradiction, right? Because this is a unit. This is a unit. Okay, so same reason for G squared plus D squared is P squared, right? So the only case must be A squared plus B squared equals P, and G squared plus D squared equals P, right? This is a very good result, right? So finally, A and B are basically, this is all the sum squares that we can find. Okay, so finally, the final theorem. Let's talk about now lemma to help the final theorem. So if P is prime of the form 4n plus 1, and we can solve the so we can solve the congruence equation. So we can solve the congruence x squared equals minus 1 mod P. Okay, so what I'm saying is that if P is a prime of 4n plus 1, then you can solve x squared minus 1. X squared equals minus 1 in the mod P. Okay, so still big example. If P is 5, and 4 is minus 1 in the mod P, right? So 2 squared. Okay. Okay, so this is the famous results. Let me just quote the results using the Wilson's theorems. Oh, so Wilson's theorem is simple. You can prove it by the Fermat little theorem. Okay, so basically your P minus 1 factorial is always minus 1 mod P. Okay, you can check for a small case. Okay. Yeah, so if you believe this, and also P is 4n plus 1, right? So let's see. Okay. Yeah, I mean, yeah. Sorry. So this is the Wilson theorem, right? So Let's let x to be p minus 1 divided by 2 factorial, right? Because yeah, okay, so p minus 1 is 4n, right? So let's see. Let's see. So this x is basically 1 times 2 times 3 up to p minus 1 divided by 2. And then you can change it into minus 1, right? So your x is also can be written as a minus 1, minus 2 up to minus p minus 1 divided by 2. And the p minus 1 is 4n, so divided by 2n, right? So they are always even times minus 1. So these two is okay. Okay, so from here that but you can also check that p minus k, p minus k is just minus k mod p, right? So that means your x squared is basically 1 times 2 times up to p minus 1 times minus 1 minus 2 up to minus p minus 1 divided by 2, right? So combine these, you get 1 times 2 times p minus 1, and then this is changed to p plus 1 divided by 2. And yeah, so this let's see, right? So this is minus k, right? So I can write this into I think it's this, right? And then keep going, you get the p minus 1. So minus 1 in terms of change to p minus 1, minus 2 in terms of p minus 2, use this. Okay, so combine all of it, you get a p minus 1 factorial. And then by Wilson's theorem, the minus 1 mod p. Okay, so final theorem. Okay, so if p is prime of the form 1 plus 1, then p equals to a squared plus b squared. AB is an integer. So now we just combine these two lemma, right? Since we already, so our goal is to find c. So our goal is to find c such that x squared plus y squared equals to cp, right? This is our goal. Which c is relative to prime, which c is relative to p, prime to p. Okay, this is our goal. Okay, so let's finish the proof. Okay, so let's combine a lemma. We just pick x squared equals to minus 1 mod p, and then we can pick x is less than we can pick s. We can restrict this x to be less than p divided by 2, right? The same argument. So let's just choose such x, right? Choose such x, and let's we can also choose. We can just define y to be p minus x. Okay. And yeah, so actually we don't care. Okay, so we just choose this, and then from here we get x squared plus 1 equals 0 mod p. Okay, right. So yeah, so this is p times something, right? P times some c. So the remaining is to control this c, right? But I already restricted px to less than p divided by 2. Okay, so that means p squared divided by 4 plus 1 equals to pc, right? But the p squared divided by 4 plus 1 is less than p squared. Okay, so c is less than p. C is strictly less than p. Okay, so c must be prime to p. C must be prime to p. Okay, so since c is prime to p, so by this original theorem, well, we get our results. Okay, that's it. See you guys in the next videos. Bye.